read, other people cannot read, so that I will not be copied from by other people. But anyway, in here, you don't have to worry about paper. That means that write clearly in the exam day after tomorrow. I don't care you're using 100 pages. Okay? Just write clearly. Don't jam it up together. Okay? Any things that we cannot read, we will do this. Okay? Do the examination like make a report to your boss as clear as you can. Okay? Don't chicken scratch. You said the time is not enough. I give you enough time. Okay. So the examination time start at 12 o'clock. We have so only 5 problems. You don't need half hour for one problem. Okay. You use a half hour for one problem. Something is deadly wrong. Okay. So that's what I want you to be aware of. Okay. So in the book, it didn't say clearly that when I'm doing this, actually when I stretch doing the work, it has a potential energy. In which case I said 1.5 kx squared. Why? When I release it, there's some velocity there. So see how fast it goes? So this is what we want to prove on the section 6.5. 6.5 is related with the work kinetic energy field. Some kinetic energy. That means if you release it, it has a velocity. So just like what I showed you in here, it's like this. So here's a velocity, motion. Motion like that. It's a motion going on. So if that is the cases, that is done by the experiment. Now we want to mathematically prove it. So why you want to mathematically prove it? Then you can use it all the time. Okay, from that on, we know the kinetic energy is represented by K equal 1.5 mv squared. This is also what we like to prove. So in these cases, we like to go back this diagram again. This is a spring, and this is have a mass. Mass push it out in this direction, then it done the work. Work is done. Work is done. Work done. And then at the same time, it store the energy. Work done and store, energy stored. Energy stored can become a kinetic energy. So we say work is equal to per se equal to F dx. In this case, xi to xf. Now, from this on, is related with your mathematics calculus in Math 5A. Calculus, Math 5A basis. Okay, now there's a F equal ma. So this explanation here, F is equal ma. And then what is A? A equal time rate change of velocity. So you go to m. In that cases is dv dt, and then this is dx. Okay, so that's what we have. Now we like to somehow we like to change the variable, change the variable a little bit. and try to solve the problem. Okay, so he says now we have a dv dt. So integration of m dv dx. We can write down mv dx. This portion we can write down dv dx and dx dt. Okay, all this is equal dv dt, called calculus. Okay, so what is dx dt? Is dx dt v equal to dx dt. So in that case, that equal to integration m and then dv dx, and then this part equal to v, and then here is dx. And dx, don't tell mathematician I did that. Right? The physics did it. Okay, cancel this. So now the variable is changed. Variable change. So that equal to m v dv. So we usually find. So that is equal to 1/2 m v sub f squared minus 1/2 m v sub I squared. So from this on, we know that when the work is done, that the kinetic energy is changed by 1/2 m v sub f squared minus 1/2 m v sub I squared. So that gives us a conclusion: kinetic energy equal to 1/2 m v squared. So now we know kinetic energy equal to 1/2 m v squared. For the spring, the potential energy is equal to 1/2 kx squared. For the spring, potential energy is 1/2 kx squared. For the kinetic energy is 1/2 mv squared. So this is being done. So the yeah. Any questions?
Yeah, what does that say? The
This one?
W whatever. Word? Oh, word net?
The word net.
Oh, okay.
The network. So the other one we are interested to say, when you're doing the work, there's slow pull, right? Nowadays the people doing work is very slow anyway. When they look at the game, they will be very encouraged to look at the game. But doing the work, they are slow. Especially when you ask them to move something, right? In my company, we have a lot of old computer there. So we have a office. In the office, a minimum of 4 or 5 old computers. I like to give away or dump it. So we have a next to 1 block away, we have some kind called electronic waste, right? Waste by parts. So I said, why don't you just give them away? This is only you by pound. This is only cost about 10 cents or 20 cents or something like that. So I said, I want to get rid of it. I don't want to leave around in the office. So you push it. That's it. The people still didn't move it. The initial inertia is too high. So when you're doing the work, you consider what we call how fast it is. So we define a term, in which case called power. When you're doing the work faster, that means you have a lot of power. So in that case, section 6.8 is called power. Again, the power definition of power is very straightforward. Power defined as equal to time rate simple the language is? You don't need to have 100 sentences to describe the interface. If you're reading the book, they using at least 4 or 5 language, 4 or 5 sentences to describe it. But that's good. That's called explanation. So you read it, you will understand it. But there's another simplification. It's called time rate change of work. In which case is equal to dW dt. The energy, the work or energy is related with unit called joule. Okay, related to time. So that creates so-called watt. So we like, I don't know who is paying the electrical bill in your houses. Anybody in here write a check to Southern California Edison? Oh God, you're still young. How nice. Is still your father and mother paying the electrical bill? Do you see the unit of the electrical bill? Yeah. The unit or electrical bill. Kilowatt hour. That's kilowatt hour times time equal to work. So what do you buy? You buy wood from Southern California Edison. Very cheap. Why? Look at this. Shut off, turn on, shut off, turn on. Can you imagine that? Takes the Southern California Edison is in Arroyo Parkway, right? So it takes how long for somebody to bring the electricity to here? It take a long time to bring the electron to here, right? Or bring the coal to here to burn the fire and getting the electricity, right? For boiling water. So from that point of view, the electricity is very, very cheap. So now, if we want to save money, then you want to change all the electrical light bulb by fluorescent lamp light bulb. In the future, you have to change all the light bulb by the LED called light emitting diode. Those are very efficient. Okay, that concludes chapter 6.